I've decided to make an entire series on YouTube, and I'm going to post it on my TikTok and Instagram too. An entire series on partial differential equations, because I've realized there's not many resources on the internet that really teach you in depth this subject. When I took it 2 years ago, I tried to find good videos for PDEs on YouTube, and I realized it's really surface level. The playlist that I found really just covered the chapters 1 and 2 of this subject. Even the MIT playlist, it was good, it was high quality, but it was not enough for you to really know what you're doing in that subject. It went over things way too quickly, and it didn't cover enough things for you to say you know everything about PDEs, at least on the undergrad level. And we're not even going to talk about the graduate level. I'm not there yet. I'm still an undergrad. So I'm just going to teach you everything I know about PDEs that I learned in undergrad at McGill University from one of the oldest PDE profs on the planet right now. I think he's over 90 now. He's been teaching for so long that our other engineering professor, who's about to retire next year, when he went to McGill University and studied mechanical engineering, he had that prof, and he already looked kind of not so young anymore. That prof these days actually looks like Einstein. So he's been teaching analytical partial differential equations for the past probably over 50 years of his life. So much that I'm convinced that there's nobody else on earth right now that knows it better than him. I was lucky enough to have him as our professor. So here I am trying to spread the knowledge as much as possible. In this first video of me trying to teach you partial differential equations, we're just going to talk about the intuition behind everything. I'm not going to teach you the formulas. I'm not going to teach you the steps just yet. I'm not going to teach you the solutions. I'm not even going to show you a number in my screen. You're just going to see my face. I want you to just really understand what is physically going on with this subject in math. I've been obsessed with this subject ever since I took it because of how it applies to so many things in the universe. It's not just for physics. It goes from physics to literally money, to the stock market. And there's a good video by Veritasium talking about this. Basically, the Black-Scholes equation in finance to predict a lot of the prices in the market is actually a derivation from the heat equation. And all of these that I just mentioned are PDEs, partial differential equations. And what partial differential equations really are is just these equations that's telling you the evolution of every parts of something as it goes through time, or as it goes through space, or as it goes through time and space, depending of the situation. So if you have a transient partial differential equation, that means that time is involved. If you have a steady state partial differential equation, that means that time isn't involved, and you're in a state where as time goes on, you have the same profile of the evolution of things throughout some variable. That's not time. Let me show you something visual, something to show you kind of what a PDE might look like. This is just a random example, a random case, all right? These are notes that I haven't posted yet, that I will be posting for you guys eventually. These are not fully polished yet. But anyways, let's go back to this graph for now. Don't worry about anything else. Just look at this graph, all right? This is an example of one of the most simple cases of a PDE. It is a 1D PDE, actually. This looks like it's 3D, right? But it's actually a 1D PDE. What I'm trying to tell you is you have an x-axis and you have a dependent axis here. You can call it the y-axis or the z-axis, is up to you. And you have a time axis, all right? So you want to look at the curve one by one as it happens, as it goes through this time axis. It evolves. You see that it smoothly changes and flattens out. This can be an example of a heat distribution as time goes on and it starts cooling and it starts stabilizing into something. It can also be information about electromagnetism. It can also be information about money. It can be information about anything you map this model to. All right? And what PDE is telling you is the change as, in this case, time goes on. Or as you travel along this axis, what's the temperature value? Or what's the electromagnetism or money value? All right. So you can see this as the x-axis, for example. This is the y-axis, and this is the time axis. And if it reminds you about ODEs, it's because ODEs is kind of the warm-up for PDEs. And PDEs is just kind of generalizing ODEs to way more variables. ODEs was kind of studying only the change of a single variable. PDEs is studying the change of a function that contains many parameters at the same time. I'm gonna give you some examples. The most common example. Let's take this ruler, all right? But now imagine it as a very thin, long bar. A metal bar, let's say. And you light up a lighter in the middle of this bar or any other point on this bar, okay? You light up this lighter, and at that point, the temperature of the bar is going to go up. And because of heat conductivity, you're going to have a temperature profile along this bar. Now, if you keep this lighter here, the temperature profile at some point is probably just going to stabilize into some profile. Now, if you take out the lighter, the temperature profile is probably just going to start stabilizing into something flat again at some point as time goes on. Now, all of these phenomena that you just heard, these temperature profiles through time, through space, they're all described by partial differential equations. And that's what this field is for, is to describe changes through time and space, and or space. When you took ordinary differential equations, you probably heard that partial differential equations was like 100 times harder than ODEs. But I'm here to reassure you about one thing. It's not really that much harder. It is harder, but a lot of the hard part was actually just you remembering your ODE operations. That was the hard part. You basically need a lot of ODEs to solve your partial differential equations. But the theory doesn't get that much more cursed. This is only a simple example, and it's only a 1D example of a partial differential equation. You can have a 2D example. You can have a 3D equivalent example of heat distribution through some object. And 2D would be a plate, 3D would be some solid 3D object. It can be a sphere, it can be a cube, it can be a parallelepiped, it can be any shape. Just the more complicated the shape gets, the more complicated the analytical solution gets, and usually we only stick to some of the most simple shapes to solve it analytically. When it gets to a really complicated shape, that's when you start solving partial differential equations, not analytically anymore, but numerically. That's a simple rule you gotta apply to everything in math and physics. When it gets really complicated, chances are there's no actual analytical solution to solving that problem. You have to do it numerically through finite difference methods. And that's also why CFD and FEA exist in the engineering field. If you don't know what it is, don't worry about it for now. But basically what it's just saying is when things get too complicated, you don't want to solve it to the infinite precision anymore. You want to solve it by separating it into more simplified chunks. In other words, analytical solutions are able to provide you an image to the infinite precision. So you can zoom in as much as you want on this image. The line is going to stay continuous for the shape of whatever object you have on this image. Now, numerical solutions basically pixelate everything, but it actually makes solving a lot of the harder problems actually possible, while analytical solutions don't really actually exist for these problems. Earlier, I only gave you a simple heat equation, heat diffusion example. There's other types of PDEs, including the Laplace's equation, as well as the wave equation. And we're not going to go into detail what they are in this episode, but all you need to know is the heat equation, the wave equation, and the Laplace equation, they're able to describe so many phenomena in the universe, including, let me read you a list: heat transfer, fluid dynamics, electromagnetism, sound waves, theory of gravitational or Newtonian potentials. There's so many things. It's everywhere. It's literally everywhere. Money too, the stock market, Black-Scholes equation. So you might ask yourself, what are the prerequisites for this course? First of all, you need to be familiar with all of calculus 1, 2, 3, and sometimes people call it calculus 4, but sometimes people just call it vector calculus. And then you need to be familiar with ordinary differential equations, and you need to be familiar with your linear algebra, especially when it comes to Hermitian operators and eigenvalue stuff, because you'll need a lot of this for the later on partial differential equations. And spoilers alert, it's mostly going to be used for Sturm-Liouville. Now, eigenvalues are going to be used since day one of partial differential equations when you solve analytically for a solution for your boundary value problems. Another big popular topic you probably need to be very familiar with is Fourier series. So if you know all of these things, you should be more or less ready to tackle this subject. Who needs partial differential equations? If you're in engineering, you probably will see a PDE in your life. You might, for some engineering branch, not actually have a dedicated course for it because you don't see it as much as, let's say, for mechanical engineers or electrical engineers. But you'll still probably see a PDE, unless you're maybe in industrial engineering something. I'm just kidding. Probably you also see it. So mechanical engineers, chemical engineers, electrical engineers, they see PDEs in their courses because electromagnetism, heat transfer, fluid dynamics, all of these subjects are just kind of little sub-branches of PDEs, really. Of course, it has their own other types of formulas that makes the subject that subject, but PDEs are everywhere. If you're in physics, you probably have PDEs too. If you're a math major, you'll for sure see PDEs also. If you're in finance, you actually study also PDEs and the higher level stuff. If you're a quant, you're an economist, there's PDEs that dictate the market, money, prices all the time. And you also study PDEs in so many other subjects that I didn't mention. Because what this subject is the subject that describes changes of things. And if you're studying changes of things and you need to put it into a mathematical model, chances are PDEs will be nearby. It is quite sad to see that a lot of schools are starting to water down their degrees, and a lot of the engineering schools that I know, let's say in the United States, or even in the ones in Canada right now, they're just taking out PDEs out of the undergraduate curriculum, which is tragic because it is a hard subject, but it is necessary. Once you understand this course, physics is way easier. You don't need to be confused anymore because that was kind of the final level of math in undergrad for engineering. It's just PDEs. Some might say that numerical methods or numerical analysis can also get quite cursed if you're really learning it in depth, but this video is not a debate about what is the hardest subject. We can just agree on the fact that there are many hard subjects out there, and PDEs is one of them. So that being said, I hope that the series is really going to help you guys, because I will be step by step showing you how to solve analytical solutions to a lot of the popular boundary value problems and a lot of the popular PDEs out there. Alright, we're going to derive things from scratch. We're going to really show what's going on here. Alright, and I hope you tune in. I hope that after this series, you're gonna ace the class. If you are already at that level where you want a PDE crib sheet, I have one that I'm selling for, I think, 10 USD or something on my Patreon. And you can go to my Patreon to overall support me. And don't forget to follow me on all platforms: TikTok, Instagram, YouTube, Patreon. Join the Discord server. It has over 10,000 people now. It's a community of students and people in STEM supporting each other, helping each other, giving each other very valuable and free resources. And yeah, join the community. Tune in. Thank you for watching the video, and see you in the next one.